After we have shown in part 2 of this series of presentations that the classical Klein-Gordon equation can directly be extracted from the Einstein-Hilbert action together with the Einstein-Field equations, and thus gives us the general theory of relativity and one of the most important quantum theories from one and the same source, we will here derive a truly fundamental and most general quantum gravity-based scalar equation. In the limit to certain metrics and curvature-free spacetimes, this equation should simplify to the classical form of the Klein-Gordon equation as it is being shown here with the usual natural constants, the mass m and the potential v. A theory of everything for which we are aiming here should not only contain Einstein's general theory of relativity, but also all major quantum equations, and it should also explain the appearance of what we describe as matter. In previous presentations in this series, we have already shown how we can extract the Klein-Gordon equation from the Einstein theory of general relativity, part 2, and that matter does not need to be postulated, part 1. Our starting point is the so-called Einstein-Hilbert action, a variational integral based on a Hamilton extremal principle. Already in 1915, it was the great German mathematician David Hilbert who derived Einstein's field equations from such a fundamental minimum principle. What Hilbert apparently did not see was that his formula, in fact, contained much more than just the Einstein field equations, but that he had also found the fundament for quantum theory. In this presentation, we will now show what Hilbert had missed, or, taking Hilbert's genius, simply not considered important enough to be mentioned at all. As we have already shown in part 1 of this series, that we do not need the matter term Lm, nor a cosmological constant to obtain matter, we set both lambda and Lm equal to 0 and just proceed with the curvature of spacetime, known as the Ricci scalar, as the kernel within our variation. Now, by following Hilbert's classical derivation, we obtain the so-called vacuum Einstein field equations. Things change, however, in a rather interesting manner when introducing a slightly adapted metric tensor with a scaling factor as shown here. Hilbert's variation now yields a much more complex kernel. Treating it like the classical Einstein-Hilbert action and demanding the whole integral to vanish gives us the quantum Einstein field equations. Thereby, the red ellipse shows us that the classical Einstein field equations are a part of the new set, making out the metric or G-related terms, while the rest is connected with the scaling function and thus the local volume of the spacetime under consideration. Taking the full kernel of our scaled Einstein-Hilbert action and assuming the gravity part to be small against the volume, we end up with a scalar differential equation. It already was shown in our earlier presentations that this equation simplifies to the standard quantum equations when we assume certain metrics. The characteristics of such metrics coincides with the typical and often used metrics like the Minkowski metric in Cartesian, spherical, or cylindrical coordinates. Here now, however, we leave the metric general. Incorporation of the functional wrapper capital F of F property, we obtain a partial differential equation on F. Please note that the integrational kernel can dramatically be simplified by demanding the scaling function to fulfill a special condition. We already treated this path in our second part of the series, where we derived the metric, which is to say the generally quantum relativistic Klein-Gordon equation. Here, however, where we insist on completely general metrics in an arbitrary number of dimensions, our result is a bit more complicated. In fact, it contains all quantum equations of non-Dirac type, whereby regarding the latter, we refer to our presentations part 3 and 12 of the series. Please note that this equation in fact simplifies to the classical Klein-Gordon equation in the case of special metrics. Comparison of the general form from slide 11, here in a slightly reordered form, with the classical Klein-Gordon equation gives us the equivalency of mass and potential in the metric, respectively the quantum gravity picture. We note that with the approach used here, we should discuss the following issues. The direct application of the Einstein-Hilbert action does not give us the perfect Laplace operator for all metrics, see slide 12. And there is no separate equation, which is to say, the equation we have found for capital F of f, even though already clearly mirroring the classical quantum equations, is only a part of the classical Einstein-Field equations. We try to solve the problem via an additional variation. This time the variation is with respect to the function f, and we apply the so-called functional derivative, for which we refer to the standard textbooks in theoretical physics. Here on this slide, we assume to have performed the f variation after the standard Hilbert variation under the assumption of weak gravity. As we see in the red ellipse, this time we obtain a perfect Laplace operator. It should explicitly be pointed out that we can obtain the same result when applying the f nudging, which is to say the functional derivation of the Einstein-Hilbert action, before the usual Hilbert variation with respect to the metric tensor. Again, we obtain the perfect Laplace operator. Introduction of a suitable condition for the Rapper function capital F gives us the quantum gravity Klein-Gordon equation. Comparison of the general form from slide 16, here in a slightly reordered form, with the classical Klein-Gordon equation gives us the equivalency of mass and potential in the metric, respectively, the quantum gravity picture. The interested reader may find more information in the books shown here or other publications of this author. We explicitly want to point out here, however, that we do not consider us the first to have found the connection. In principle, namely, it was all already inside Hilbert's ingenious approach, and he only could not see it because, at the time he wrote down his equation, the fundamental equations of quantum theory were not yet discovered, and his main goal was the derivation of the Einstein-Field equations, and thus, as Einstein had not bothered about also finding quantum equations inside his General Theory of Relativity, Hilbert, as a mathematician, obviously saw no need to consider the broader spectrum residing in his approach. These new insights open up a variety of possibilities for the most astounding developments, be it inexhaustible sources of energy, future weaponry, metric artificial intelligence, quantum gravity computing, or completely new, and what is much more important, truly unbiased and most holistic modeling tools for almost all sorts of problems. And how could such developments be realized? The optimum is the global approach aiming for the quantum gravity computer and naturalized AI, which is a Manhattan-sized project. How this disrupts everything and makes the owner the global monopoly to just everything can be extracted from the material presented in this talk. Next smaller step is just the naturalized AI, which still is a small Manhattan project. This too already reaches very far and propels the owner into a global monopolistic and long-time leading position, unless somebody achieves a takeover via a working quantum gravity computer tech. Everything else are service projects.